Okay, so thank you everybody for attending this IFT webinar. Today we have with us Ningqiang Song from the Queen's University and Perimeter Institute, and he will speak about microscopic black holes in neutrino telescopes. Thank you.
Thank you, Michele, for the opportunity to present my work. I will mainly talk about the microscopic black holes inspired by large actual dimension models and how they would affect the observation at the neutrino telescopes, colliders, and especially what are their imprints in cosmology. So here is the outline. I will give a very brief introduction about large actual dimension models, and then I will talk about the discovery of microscopic black holes at the neutrino telescopes. And then I will talk about how can we discover dark matter through these black holes at the colliders. And then after that, I will introduce the black hole imprints in the early universe. And finally, I will give a brief conclusion. Okay. Large actual dimensions were proposed by Atani Hamid, Demopoulos, and Devali in 1998, which says that the standard model particles are confined to the three-dimensional brane. This means that our usual three-dimensional world, this includes standard model leptons, quarks, gauge bosons, Higgs, etc. But the gravitons are very special. They can propagate in the bulk, including actual dimensions. So if we look at Gauss's law, we'll be able to derive the gravitational potential at a really, really small distance, which means that the distance is much, much smaller than the size of the actual dimension. There, the gravitational potential is proportional to 1 over the distance to the power of n plus 1, and n is the number of actual dimensions. But at a really, really large distance, for example, in our real three-dimensional world, we see the gravitational potential is still proportional to 1 over r. It scales with the inverse of the distance. So we can match these two different potentials at a distance which is equal to the size of the actual dimension. Then in this case, we see the four-dimensional Planck scale, or our regular Planck scale squared, is proportional to the production of the bulk Planck scale and the size of the actual dimension to some power. And if the size of the actual dimension r is large enough, we see the bulk Planck scale m star can be as low as a few TeV. This is far below our regular Planck scale, and this will solve the hierarchy problem. There is one important implication of this kind of large actual dimension models, which is the production of microscopic black holes in particle collision. Hoover conjecture suggests that if the impact parameter between two colliding particles is smaller than 2 times the horizon radius of the black hole, we can actually produce black hole in particle collision, which means that we can squeeze a really large amount of energy within a very small space. And in that case, we can actually produce black hole. This is equivalent to say if the center mass energy of the colliding particle is larger or much larger than the bulk Planck scale, we can produce black holes from there, but they have to be microscopic. So we can look at several possible scenarios. For example, there is the scattering between high energy cosmic neutrinos and nucleons, like in the IceCube detector, where the center mass energy can be really, really high. Or we can also detect high energy cosmic rays, like in the atmosphere when there is high energy proton colliding with the nuclei in the atmosphere, we can also produce these black holes. Or we can also look at the cosmic ray collision during the age of the universe. And also, if the central mass energy is high enough at future colliders, we can also expect black holes to be produced in PP collision. In the early universe, if the reheating temperature is really, really high, so we can naturally expect these black holes to be produced in the hot plasma of the universe. So if we look at the PP collision, we have to integrate over the pattern distribution function of the protons, because at such kind of high central mass energy, we actually expect the patterns in the protons to collide with each other, not the protons themselves. From that, we can integrate over the cross-section pi times B max. Because these large extra dimension theories can predict the production of black holes, we can also constrain these kind of models from the non-observation of these black holes. For example, in LHC, we found that the bulk Planck scale has to be larger than 5 to 10 TeV, depending on the number of extra dimensions. We also have other constraints from the test of gravitational force at a really, really small distance, or the supernova and neutron star cooling. It was proposed by Akane Hamad in his first papers that n equals 1, which means one extra dimension is strongly excluded by the gravity at the solar system scale, because this is very well measured. We can look at some useful energy scales. The central mass energy of 5 TeV in high-energy neutrino-nucleon collision would correspond to the neutrino energy of 13 TeV, which means that the neutrino has to be higher than this energy in order to produce black holes in the neutrino detector. If we look at LHC, it is operated at central mass energy of 13 TeV right now. And in the future, when it is upgraded, probably we can reach the central mass energy of 100 TeV. And also a fundamental limit is the GZK cutoff, where the proton energy has to be smaller than 50 eV in the high energy cosmic ray. And if we look at the collision between such high energy cosmic ray and the protons, like in the atmosphere, then the central mass energy would be roughly 300 TeV. Once these black holes are formed, they will decay through Hawking radiation, and the decay is through all kinds of channels, including all possible degree of freedom, like Higgs, gluons, gauge bosons, leptons, quarks, all these standard model particles, but also gravitons and other beyond standard model particles, even dark matter. But gravitons are very special because they can propagate in the bulk. That means the emission of gravitons can be directed into the bulk, not in our three-dimensional world. If we look at the Hawking temperature, it depends on the number of extra dimensions, the mass of the black hole, and the fundamental Planck scale and star, which is very different from the four-dimensional case. And on the left, I show the Hawking temperature as a function of the black hole mass. We see if the black hole mass is much, much larger than the fundamental Planck scale. For a larger number of extra dimensions, we expect higher Hawking temperature, and things are opposite for very small black holes, where n equals 1 actually predicts the highest Hawking temperature. And Hawking radiation is featured with the gray-body distribution spectrum. So if we look at this equation below, there is a prefactor which is called the gray-body factor, and the gray-body factor is also different from the four-dimensional case, so that we have to solve for them separately. After the introduction, I will talk about the discovery of microscopic black holes at the neutrino telescope. But first, let's look at the high-energy neutrino flux. IceCube has been operating since 2010, and it has detected a lot of atmospheric neutrinos above the energy of GeV. And these neutrinos have been used to study the neutrino oscillation parameters. At high energy scale, like about 10 TeV, IceCube has also detected a lot of events, and these are the so-called HES events, or high energy starting events. As it goes to energies even above that, the simple power law that is obtained by the IceCube collaboration may not be valid strictly, because there we also expect the resonant neutrino production from the collision between high-energy cosmic rays and the starlight, or even CMB. And there, the neutrino flux is also really, really low. So we really need really large detector with a very large exposure in order to detect these neutrinos. Ground is an option. It's a radio array in the mountains, and it can detect the radio emission from tau decay, and these taus are produced by tau neutrino charged currents in the mountain. And when these taus exit the mountain, they can decay and produce radio emissions, and it has really, really large exposure, and it can detect neutrinos with energy up to EeV or even above that. I will also mention two possibilities here. One is IceCube generation 2. We know IceCube is a Cherenkov detector in the Antarctic. It is like 1 meter deep in the ice, and it is really large. It is usually compared with the Eiffel Tower to show how large it is. But in the future, in like in 2040 and 2050, we would expect IceCube generation 2, which is about 10 times larger than IceCube. Also, we can expect IceCube generation 2 radio array. If you look at the panels, the area of the panels below, we see that the generation 2 radio arrays are even much, much larger than IceCube generation 2, which will allow us to detect more ultra-high energy neutrino events. The other is the Pacific Ocean neutrino experiments, or the so-called P1. It uses a similar technique as IceCube, and it has some strings in the Pacific Ocean near Vancouver, and it will also collect the Cherenkov light with some strings. It is partly funded by McDonald Institute, but we expect the exposure also to be much, much larger than IceCube. Depending on the production mechanism, the neutrino flavor composition at the source can be very different. For example, if neutrinos come from neutron decay, we expect only electron neutrinos at the source. So the flavor ratio for electron, muon, and tau neutrinos will be 1:0:0. If neutrinos come from pion muon decay chain, we expect the flavor ratio to be close to 1:0. And if it comes from muon suppressed pion decay, which means that there is only muon neutrinos produced at the source, we expect the flavor ratio to be 0:1:0. But because these neutrino sources are very far away from the Earth, we expect these neutrinos to undergoing neutrino oscillation and lose their coherence when they arrive at the Earth. And because these neutrino oscillation parameters are very well studied as a bunch of Earth experiments, we expect the neutrino flavor detected at the Earth after oscillation is constrained to a very narrow or a very small island, which is not very far away from 1:1:1 equal flavor ratio. In the detector, we don't see these high-energy neutrinos directly, but we only see their interaction products. An example is the track events at IceCube, which may be produced from muon neutrino charged current interaction. And in this kind of interaction, muon neutrinos scatters with the protons of the neutrons in the nuclei, and then muon neutrino is converted into a muon. But at the same time, the nuclei is fragmented into a bunch of hadrons. These hadrons will initiate some shower, and these muons will lose their energy stochastically when they travel outside the detector. So we'll see a very long track in the IceCube detector. Not only muon neutrinos, but in the future, if we have larger exposure, we can also see tau neutrinos, which can produce tracks. This happens when tau neutrinos are very energetic, which produce very high energy tau, and these taus will also lose their energy and produce track in the detector. But in that case, because tau is much more massive than muons, so we expect at the same energy, these tau tracks are more faint or not quite visible as the muon tracks. Another very useful and very frequently seen topology is the shower events. It can be produced by electron neutrino charged current events or the neutral current interactions from all neutrino flavors. This kind of topology looks like a spherical blob, which expands from the interaction vertex outwards as the time goes on. It can also be produced in tau neutrino charged current events, and if the tau is not very energetic, it will decay almost immediately after the first interaction vertex. In this case, it will produce a single shower. But if the tau energy is really, really high, we expect it to travel certain distance, probably larger than 100 meters, and then decay. If it decays to electron or hadrons, the decay products will produce another shower. So in IceCube, we can probably see two different showers that can be separable from each other. This is the so-called double bond events. So let's look at black hole decays. It is very interesting because it can decay into all kinds of leptons, electrons, muons, and taus, also hadrons. So we expect all standard model topologies to be produced in black hole events. One may question, what is the probability to produce a black hole in high-energy neutrino-nucleon scattering? For that, we can look at the cross-section. We see the cross-section really depends on the number of extra dimensions, but most importantly, on the fundamental scale or the Planck scale. If the Planck scale is 3 TeV, we see the black hole production at high energy is comparable or even larger than the standard model case. But if the Planck scale is 10 TeV, then the production cross-section is much, much lower than the standard model case. For illustration purpose, here we look at the reconstructed flavor composition at the IceCube, assuming the Planck scale to be 3 TeV. And we see from the table below that we expect more shower and more track events than the standard model case, and less double bond events. This is mainly due to the energy asymmetry condition, which I will explain in a moment. We also expect more tracks because there are more muons and taus from the black hole decay products. All these actually position the standard model plus black hole contours to the upper right corner of this flavor triangle, and we see the 1-1-1 equal flavor ratio is excluded at more than 2 sigma in our analysis. But as I mentioned before, the bulk Planck scale is constrained by LHC, and the bulk Planck scale has to be larger than 5 to 10 TeV. In that case, we don't expect so many black hole events to be produced at IceCube. So the question is, if we observe one event, how can we distinguish a black hole event from a standard model event? In that case, it is important to look at the differential cross-section. In this figure, I show the differential cross-section in the standard model case. This is plotted as a function of y, and y is defined as 1 minus the final lepton energy divided by the incoming neutrino energy. We see, because this figure is in log scale, the cross-section actually peaks at really small y, which means it peaks at a really large final lepton energy, which means that most of the incoming neutrino energy is actually transferred to the final state, lepton or neutrino, not these hadrons. The things are very different if we look at black hole production and decay. In case of a black hole is produced, it can actually decay into 6 to 10 primary particles on average, and the lepton is only one of the decay product. So we expect the lepton energy in that case to be much smaller than the final state lepton in the standard model interactions. This will enable us to distinguish black holes and standard model events by the energy distribution of a specific topology. If we look at muon tracks, on the left, I show the muon energy as a function of the shower energy. I did some Monte Carlo here, assuming different bulk Planck scale. We see the standard model events are located on the upper left, and the black hole events are in the lower right, which means that in the standard model case, the muon energy is supposed to be much larger than the energy of the hadrons which initiates the shower. And in the black hole case, the things are opposite. We expect the hadrons to be much more energetic than the muons, because muon is only one of the black hole decay product. So this enables us to conclude that we expect a lower check energy to shower energy ratio in black hole events than in standard model case. We can also look at double bond events. As I mentioned before, if the tau is energetic enough, when it is produced from tau neutrino charged current interaction, it can travel certain distance and then deposits its energy there as a second shower. In the standard model case, the tau is much more energetic than the hadrons, so we expect the second shower from the tau decay to be more energetic than the first shower. But in the black hole case, we expect the first primary shower to be more energetic than the secondary shower produced from tau decay. So this allows us to define the so-called energy asymmetry factor, EA, which is defined as the energy of the first shower minus the energy of the second shower divided by the total shower energy. And if we look at the second bound energy as a function of the first bound energy, very similar to the check case, the standard model events are in the upper left and the black hole events are in the lower right, which means that in the standard model case, the first bound energy is less than the second bound, and in the black hole case, the first shower energy is larger than the the second shower. If I want to make some analogy here, I would say this kind of the second bound energy versus first bound energy figure is very similar to a chocolate ice cream bar, and the candies are these colored candies are the black hole events on this ice cream bar. Just some joke there. Okay, so if we make a plot of the EA factor, the energy asymmetry factor, we see the standard model events are on the left and black hole events are on the right, which means that standard model interactions are featured with mostly negative energy asymmetry factor, and the black hole events are featured with mostly positive energy asymmetry factor. That's why when we look at the reconstructed flavor composition, we expect very few black hole double bonds because we implement the cut from the energy asymmetry condition inferred from the distribution of energy asymmetry in the standard model case, where the black hole distribution actually doesn't fit into this kind of distribution. I talked about checks and shower, checks and double bonds, but we can also say something about shower events. For this, we can look at the timing information of the Cherenkov light. After the interaction, like in high-energy neutrino-nucleon interaction, we expect the final state particles to deposit their energy promptly within 0.1 microseconds. This is the dominant peak, which can be seen in the figure above. And these high-energy final states will cascade down to low-energy muons and neutrons. These low-energy muons will decay at 1 to 10 microseconds, producing a secondary muon decay echo. And these neutrons will be captured at 200 microseconds, producing a third neutron capture echo. To see how this is true, we use Flux to propagate a bunch of different particles in the S. These include pions, protons, neutrons, kaons, electron positrons, and gamma. We see this timing spectrum can actually be categorized in two groups. One is electromagnetic shower, which is initiated by electron positrons or photons. These are featured with very few muons and neutrons in the final states. And the other is the hadronic shower, which is produced by all kinds of hadronic particles. And these particles end up with copious muons and neutrons in the final states. So if we compare these two kinds of spectrum, we see the hadronic shower has some muon echo or neutron echo, which is actually 10 times larger than electromagnetic showers. We also find that the muon echo and the neutron echo are very closely correlated, and we can figure out one from another. This kind of separation can actually allow us to put different neutrino interactions into different regions. If we look at the third to first peak ratio as a function of the first peak energy, just to remind people a little bit, the first peak is the prompt peak, which dominates the shower, and the third peak is the neutron capture echo. And we see because in neutral current interaction, the final states are mostly hadronic, so we expect a really large third to first peak ratio in neutral current interactions. And in electron-neutrino charged current interaction, where we can produce very energetic electrons or positrons in the final states, the shower is almost purely electromagnetic, so we expect the third to first peak ratio to be really, really low. For black holes, the decay products are a mixture of electron positrons and hadrons. So we expect the peak ratio to lie in between neutral currents and the electron neutrino charged current events. Another important thing to keep in mind is that in the black hole production case, black hole will deposit almost all its energy in the detector, which means that almost all the incoming neutrino energy is deposited into the detector. So we expect like a larger first primary peak in black hole production case than in the standard model case. As I mentioned before, black holes can decay into all kinds of particles, so we expect all standard model topologies to be produced in black hole events. But because a black hole can decay into multiple particles and all kinds of particles, can we expect very new and unique topologies to be produced in IceCube-like detectors, which are never seen in the standard model case? The answer is yes. I give some examples here. So if the black holes decay into multiple muons or taus, and these muons or taus leave several tracks in the detector, we expect something called multi-track. If the black holes decay into multiple taus, and these taus decay inside the detector, and these showers are separable from each other, we see multiple showers, which is the so-called the N-bound events. And if these tau decays are associated with one or more muon or tau track, we see something similar to a bulb. And if one of the black hole decay products is energetic enough to produce another black hole, we see the double black hole band. The observation of one of these events would be smoking gun evidence of the production of microscopic black holes in IceCube-like detectors. But the question is that if we don't observe these events, how can we tell whether or not we have produced black holes only from the shower track and the double one events? So the flowchart of the analysis can be seen here. First, we have high-energy cosmic neutrinos. These neutrinos can interact in the detector, produce either a black hole or standard model products. If it is a black hole, we will use BlackMax, a modified version of BlackMax, to simulate the production and decay of these black holes. And then the black hole decay products are fed into Pythia to simulate the fragmentation, hadronization, and the decay of heavy particles. If it goes through standard model interactions, we will calculate the differential cross-section and determine the final energy distribution of the particles. And then again, we use Pythia to simulate the hadronization of the standard model interaction products. If tracks are produced, we will go ahead and calculate what is the track energy to shower energy ratio. If double bonds are produced, we will calculate the energy of the first bond and the second bond, and then calculate the distribution of the energy asymmetry factor. If showers are produced, things are more complicated. We will use Flux to simulate the propagation of these final state particles and collect the Cherenkov lights to produce the light spectrum. And from there, we can build the distribution of the third to first peak ratio. And then from there, we can compare these shower, track, and double one events and see how different the the energy distribution of these events would be in the standard model and in the black hole events. And then we can build the likelihood from there to see what is the prospect to discover or exclude black hole production in future neutrino telescopes. In this figure, I showed the number of observations required to discover black holes as a function of the fundamental scale or the bulk Planck scale. We can focus on the crossing points between the IceCube generation 2 line and the P1 line with these blue lines. At the 3 sigma confidence level, we see if the bulk Planck scale is smaller than 5 TeV, we can see black hole at IceCube generation 2 as a 3 sigma significance. And if the bulk Planck scale is less than 3 TeV, we can see these black holes in P1 detector. If we have larger detectors with larger exposure so that we have more statistics, certainly we can put the limit further and further. We can exclude or discover higher and higher bulk Planck scale. But keep in mind here, we only take into consideration the regular check, shower, and double one events. If we really see one of these very new and exotic topologies, we will conclude from just one event that we have discovered black holes already in future neutrino telescopes. Okay, with black holes in neutrino telescopes. Next, I will talk about how we can discover dark matter through these microscopic black holes at future accelerators. We have a bunch of evidence of dark matter, mostly from cosmology and from astrophysical observations. We can infer the property of this dark matter from the bullet cluster and from the galaxy rotation curve, and especially from the anisotropies of CMB spectrum. We know dark matter makes up about 27% of the energy budget of the universe, and of all the matter, about 85% of the matter is dark matter, and dark matter is weakly interacting at relatively large scales. If dark matter are fermions, we expect their mass to be larger than 100 to 200 electron volts due to Pauli exclusion principle. If they are bosons, we expect their mass to be higher than 10 to the minus 22 to 10 to the minus 20 electron volts because of the halo structure. From these constraints, we have all kinds of dark matter candidates. If dark matter is heavier than the black hole, than a star, it can be black holes, primordial black holes. If they are really, really light, they can be ultralight dark matter, like feebly interacting dark matter, and QCD axions. If they are in between, they can be WIMPs, although they are largely excluded by all kinds of direct detection experiments, or like asymmetric dark matter, or some other kind of dark matter. Very exciting news has been reported by the XENONTIT collaboration, where they have observed the excess of electron recoil events in the energy range of 1 keV to 7 keV. Over the last 2 or 3 months, there has been more than 80 papers trying to explain the excess, and the number is still growing. Possible interpretations include large neutrino magnetic moments and non-standard neutrino interactions, although these are subject to astrophysical and cosmological constraints, as well as solar axion and the dark photons. These are also not very consistent with the stellar cooling bond. We also have some candidates like XENONTIT particles or dark photon as dark matter, or even boosted dark matter. Bramante and I proposed the exothermic dark matter as a possibility. Anyway, as proposed by the XENONTIT collaboration, it can also be explained by possible tritium background, and we also need future experiments and investigations to confirm or exclude that possibility. Apart from that, and some other indirect hints, all the evidence of dark matter remain in its gravitational interaction. So there exists the possibility of the nightmare scenario when dark matter and standard model only interact via gravity. In that case, it would be really hard to detect these neutrinos via direct or indirect interactions. But here, I will show that we can still probe this particle dark matter if large extra dimensions exist. I mentioned in previous slides that if the central mass energy in future collider is high enough, we can actually produce microscopic black holes as future colliders. And then they will decay into all kinds of particles, including standard model and beyond standard model particles. Here we can focus on neutrinos, gravitons, and dark matter, which only interact very weakly with the standard model particles, and they may not be seen in future colliders. So for dark matter, they will adapt to the missing transverse momentum in the detector. We can give some examples here. If there is only 1 degree of freedom in the dark sector, we say dark matter is scalar. If we have 4 degrees of freedoms, we say that dark matter might be direct fermions. If we have 20 degrees of freedom, we can construct some simple dark sector. If we have 118 dark matter degree of freedoms, probably the dark matter is a copy of the standard model, like the mirror dark matter. We can construct a quantity which is the fraction of the invisible decay, defined as the degree of freedom of neutrinos, gravitons, and dark matter, divided by the total degree of freedom, including visible particles and invisible particles. As the number of dark matter degree of freedom increases, the fraction of the invisible decay also increases, as we expect. As the number of extra dimensions increase, we also expect this fraction increases because we expect some more emission degree of freedom for gravitons, because gravitons can actually emit to the bulk. So in the detector, if we look at the transverse momentum, we see the black hole signature is very different from the standard model proton-proton collisions. Black hole events lie in the region where we have high transverse momentum and high multiplicity, which can be clearly separable from the background events. So if we look at the missing transverse momentum, including dark matter, we see we can see from these colored bars here, we see if we increase the number of dark matter degree of freedom, the mean missing transverse momentum rises sharply as the dark matter degree of freedom increases. From there, from these different distributions in the missing transverse momentum, we can actually build the likelihood to see how many black hole observations are required for us to probe the dark sector in future colliders. This is shown in this figure, and different bands correspond to different dark matter degree of freedom. On the right, we show the pessimistic case where we have 4 degrees of freedom in the dark sector. In that case, we will need about 10,000 black holes to resolve the dark sector. On the left, if we have 118 dark matter degree of freedom, like in the case of mirror dark matter, we only need 100 black holes to probe the dark sector. In any case, these are all well within the luminosity reach of future colliders, unless we have only 1 dark matter degree of freedom, which means dark matter is a scalar. In that case, we're hopeless. We cannot discover this dark sector within the luminosity reach of future collider, which is about 10 to the 42 inverse centimeter squared. So finally, I will talk about microscopic black holes in the early universe. If the reheating temperature is not far below the Planck scale, because of Boltzmann distribution, we still expect some high-energy particles in the tail of that distribution. So we still expect some microscopic black holes to be produced in particle collisions in the hot plasma in the beginning of the universe after inflation. On the left, I show the black hole mass as a function of the plasma temperature. We see if the black hole Hawking temperature is less than the plasma temperature, these black holes will accrete instead of decay. This is very different from the black holes in neutrino telescopes and in future colliders, where they will decay almost instantaneously. We can also see from this figure that the black hole accretion is almost very immediate, and they grow from a very, very small mass right above the bulk Planck scale to a very high mass, up to like more than 10 to the 20 grams. And the final mass of these black holes after accretion only depends on the temperature of the plasma when it is produced. But of course, it depends on the number of extra dimensions and the bulk Planck scale. We also show an example of the mass spectrum of these black holes produced in the early universe. These black holes are associated with very different Hawking temperatures, so their lifetimes are supposed to be very different from four-dimensional black holes. In this figure, I show the lifetime as a function of the black hole mass. Without extra dimension, the four-dimensional black holes are shown in this dashed black line, and the solid lines correspond to different number of extra dimensions. We see most of the case, actually the lifetime of the black holes in extra dimensions can be much longer than the regular four-dimensional black holes. If these black holes are produced in the very early universe, they can decay into all kinds of particles. Especially, they can decay into primary or secondary photons. And these photons will modify the extragalactic photon background. And these X-ray or gamma ray photons can be detected in photon detectors like a Comptel or Fermi-light. In the figure on the top, I showed the constraints on these black holes from the extragalactic photon background. And this figure only shows the case of four-dimensional black holes. Below, I show the fraction, the constraints on the fraction of the of the primordial black holes, assuming different number of extra dimensions. This is from Johnson's paper, but we also got similar results. We see actually the shape of these constraints look very similar to the four-dimensional case, the four-dimensional regular black holes, but these peaks are shifted, or we can say these constraints as a whole are shifted compared with the four-dimensional case. These peaks correspond to these black holes that evaporate right until today. So because these black holes have a different lifetime, we expect different mass. We expect black holes with different mass to evaporate right until now for different number of extra dimensions. This is why we see these shifts. And these black holes can also evaporate and inject energy into the plasma in the universe. And then this energy injection, especially electromagnetic energy injection, will increase the free electron fraction. So this will increase the Thomson scattering along the line side for CMB photons. Effectively, it will reduce the amplitude of the CMB anisotropy at high multiples. On the left, I show how the anisotropy would change for black hole with a larger fraction and with a very small fraction. Or we can say if the black hole fraction is 10 to the -9, it will not affect the anisotropy spectrum. And we clearly see the reduction of the high multiple anisotropies. From there, we can constrain the fraction of black holes from the CMB observations. To do that, we implement the decay of these extra dimension black holes with a modified version of EXO class, and it can be interfaced with Monty Python to infer the posterior probability distribution of the fraction of these black holes. I give one example here, which is the black holes of mass 10 to the 14 grams and 4 degree of freedom with a Planck scale of 10 TeV. And in that case, we see a fraction of 10 to the -7 is greatly excluded if we consider the CMB observations. In the future, we will run a bunch of different black hole mass with different number of extra dimensions, different bulk Planck scale to see where the constraint is. Oh, good. So I will give some brief conclusions at the end. I talked about the microscopic black hole production at the neutrino telescopes. And showed that they are featured with unusual reconstructed flavor compositions, and the energy distribution is also very different from the standard model checks, showers, and double bonds. Apart from that, we also expect very unique and new event topologies at IceCubes and the IceCube and the IceCube-like detectors, and the observation of one of those events will be enough to say the discovery of these black holes. In the future, we can probably look at radio telescopes and even Cherenkov telescopes, and how the observation of high-energy cosmic rays would tell us the production of black holes or not. After that, I talked about how we can study dark matter from the production of microscopic black holes at future colliders. For that, we can look at the missing transverse momentum signature and how the black hole production will change the distribution of the missing transverse momentum. We have some ongoing work focusing on the dark matter mass and spin, because the mass and the spin will affect the gray body distributions of these dark matter particles and the production probability of these particles at future clusters. In the early universe, we naturally would expect these black holes to be produced in the hot plasma, but very different from the neutrino telescope and from the clusters. These black holes may accrete when they are produced, and they can grow into very massive black holes. When they decay, they will inject photons and other particles into the plasma, which will affect the photon background we can detect today, as well as the CMB spectrum. We also have some ongoing work focusing on the BBN and some other cosmological observations. From these cosmological observations, we can go back and constrain the Planck scale and the number of extra dimensions. Another very interesting and very exciting possibility is that if these black holes decay into dark matter, could they make up all or parts of the dark matter relic abundance that we can see in the universe today? And also, if they stop evaporation above the Planck mass, above the fundamental Planck mass, can the Planckian remnants behave as dark matter today? This will be all very interesting and very optimistic, very exciting possibilities or scenarios that we can explore in the future. So stay tuned. I will stop for now and take questions. Thank you.
Okay, thank you very much. Are there questions? Yes. Sven?
Yes, hi. Thanks for this nice overview about all the possibilities to observe these microscopic black holes. Sorry. In the beginning, as a motivation, you were talking about, oh, maybe I should put on my camera that you can see me. So, hi. In the beginning, you were giving the motivation that the theories of large extra dimensions may solve the hierarchy problem, etc., and this connects the scale, the Planck scale in these theories, which is of course then important for your black holes. Now, so far, all the searches were negative. Yeah, we haven't heard of any discovery in this respect. Also pushing the limit further up. Yeah, the scale that may be allowed in this kind of theories. At some point, I guess the original motivation that you solve the hierarchy problem will be eliminated by the non-observation of black holes if there is not a discovery. So how do you see the status right now, and how do you see the status with the future experiments that you are also mentioning, like FCC, HH?
Right. So you are indeed right. Initially, this was proposed to solve the hierarchy problem, and especially if R, the size of the extra dimension, is really, really large, and we see the Planck scale is not very far away from the electroweak scale, and then so that we only have one scale in the UV theory, which is the electroweak scale. But then because the non-observation of these theories, the non-observation of these black holes and also KK gravitons, we are pushing the limit to higher and higher Planck scales. And now, right now, the limit is about 5 to 10 TeV, which is still not very far away from the TeV scale. But in the future, certainly we will expect we can push the limit further. There's one possibility that we will discover black holes like in future colliders, because in the future the central mass energy at future collider will be about 100 TeV, and also if we have larger detector, we can reach very high central mass energy in future neutrino telescopes. And if we can discover black holes there, this is amazing. We can really study dark matter and very exciting new physics from there, from the production of black holes. And if not, there is still one possibility, which is that we really have many extra dimensions. So if the number of extra dimensions is really large, so if the number of extra dimensions is really large, actually it's really hard to exclude these black holes because the Hawking temperature is really low. So in that case, as you can see, if we increase the number of extra dimensions, the bulk Planck scale, we can limit is actually 5 TeV compared with like 2 TeV, like 10 TeV in the 2 extra dimension case. So that means in the collider, if we have more and more extra dimensions, it is actually really hard to limit these extra dimension, this Planck scale in the future colliders. But if we take the 2 extra dimension as an example, and if we can really reach the central mass energy in future colliders, we will be able to exclude the bulk Planck scale like at the order of about between 80 and 100 TeV, which is very exciting. And not just the extra dimension theory, we can actually discover or exclude many different beyond the standard model scenarios if we really go to such high central mass energy, because it will allow for the production of all these heavy particles in the colliders.
Okay, thanks.
Okay, more questions? Okay, so let me thank you for this very nice and very interesting talk, and everybody who attended for participating to this webinar. Thank you very much.
Thank you.